Imagine simulating how a shockwave travels through a material, or how air flows over an airplane wing, or how heat spreads through a reactor core. These are partial differential equations, mathematical monsters that describe real-world physics. But solving them, it can take hours, even days, on supercomputers. And if you're trying to optimize a design, test hundreds of scenarios, or run real-time control systems, that's not just slow, it's impossible. But what if we could build a super-fast shortcut, a smart, lightweight model that predicts the same outcome in milliseconds? That's the power of reduced-order modeling, and today we're diving into a breakthrough in this field, Higher-Order LaSDI. Traditional reduced-order models, ROMs, work by finding patterns in data. They learn that the system's behavior lives on a much simpler, hidden shape, a low-dimensional manifold, and then model just that. Think of it like this. Instead of watching every single pixel in a movie, you only track the movements of a few key characters. You still get the story, but in a fraction of the time. But here's the catch. Most ROMs assume the system behaves like a first-order equation, like a simple spring or a falling ball. But many real-world systems, they're higher order. Think of waves, vibrations, or electromagnetic pulses, where the acceleration or jerk matters just as much as position or velocity. That's where higher-order LaSDI, or HLaSDI, comes in. HLaSDI is a game-changer. It doesn't just model the solution, it models all its time derivatives. For a system with k time derivatives, HLaSDI uses k separate neural networks, each trained to encode a different layer of the system's evolution. One network learns to encode the position. Another learns the velocity. A third learns the acceleration. And so on. Then, instead of treating these as separate signals, HLaSDI unifies them into a single, powerful latent dynamic system, a high-order differential equation that captures how the entire system evolves over time. It's like having a single brain that understands not just where the car is, but how fast it's going, how hard it's accelerating, and how all those things are connected. Here's where it gets really clever. Most models only train to be locally accurate, to match the data at each tiny time step. But that's like teaching a driver to only steer correctly at every single turn, without thinking about the full journey. HLaSDI fixes this with a technique called Rollout Loss, where the model is trained to predict the future, not just the next frame, but any future frame, anywhere in time. It's like training a self-driving car to not just follow the road, but to plan its route 30 seconds ahead, anticipating curves, traffic, even construction. And HLaSDI doesn't stop there. It uses chain rule and consistency losses, mathematical rules that force the model to understand the relationships between derivatives. If velocity is the derivative of position, the model must learn that. It's not just guessing, it's learning physics. Let's see it in action. In one experiment, HLaSDI predicted wave propagation on a complex, star-shaped domain, something with irregular geometry and non-uniform time steps. It used only 11 training data points, just a tiny fraction of the full parameter space. And yet, its predictions were within 1.6% error for the wave's position, and 4.2% for velocity, in just 0.031 seconds. Compare that to the full simulation, which took 1.24 seconds. That's a 40 times speedup. And it didn't just work on waves. It nailed the Klein-Gordon equation, a relativistic wave equation from quantum physics, despite a wildly oscillating, multi-frequency initial condition. Only 9 training points, and it predicted the full solution with under 8% error. One of the most powerful features, uncertainty-aware training. HLaSDI doesn't just guess where to sample next, it knows where it's most uncertain. Using Gaussian processes, it identifies the most confusing parameter values, where its predictions are least confident, and focuses on learning those first. It's like a student who says, "I don't understand this part, let me study it harder," and the model does exactly that. This means fewer simulations needed, faster convergence, and higher reliability, even without ground truth. So what's the big picture? HLaSDI isn't just a faster simulator. It's a new way of thinking about physics-based modeling. By embracing higher-order derivatives, mathematical consistency, and adaptive learning, it extends the reach of reduced-order modeling into domains that were previously out of reach: hyperbolic PDEs, vibrational systems, relativistic wave equations. It's not just faster. It's smarter. It learns the structure of the physics, not just the numbers. From fluid dynamics to quantum mechanics, from climate modeling to aerospace design, HLaSDI is opening the door to real-time, high-fidelity simulation. And the best part? You don't need a supercomputer. Just a few data points and a little math. This is the future of scientific computing. Ever wonder how computers and mathematicians estimate derivatives, like the slope of a curve, when they don't have a perfect formula? Today, we're diving into a powerful mathematical trick, mixed difference approximations, a way to estimate derivatives using function values at cleverly chosen points. And yes, it's not just theory. This is how numerical methods power everything from weather forecasts to video game physics. Let's say you want to estimate the second derivative, basically how fast the slope is changing at a point x. You don't have a formula, but you do have values of the function at nearby points. Maybe x minus a, x plus b, and x plus b plus c. Sounds messy. Not with the right math. Here's the big idea. We use Taylor expansions, a way to approximate functions using their derivatives. Think of it like building a Lego model of a curve piece by piece, using information about its height, slope, curvature, and so on. So we expand each function value around x, up to the fourth order, to capture fine details. Then we combine them with unknown coefficients, C0, C1, C2, like weights in a balance. Our goal? To make this weighted combination equal fx plus a tiny error. So we set up a system of equations. We want the coefficients of fx and fx to vanish, because we don't want those terms messing up our second derivative, the coefficient of fx, to be exactly 1 and the rest. That's where the error comes in. This gives us a linear system, like solving a puzzle with 4 equations and 4 unknowns. After some serious algebra, what we call row reduction, we get the exact coefficients. They look complicated, but they're not random. They're carefully tuned to cancel out unwanted terms. For example, the weight on f, x minus a, ends up being 2b plus c. And the one on f, x plus b plus c, minus 2b minus a. Now here's the magic. Once we plug these weights in, the approximation becomes cf x minus a plus c0 f, x plus c1 f x plus b plus c2 f x plus b plus c, approximately f, x. With an error that's proportional to h2, where h is the largest step size, the biggest gap between any 2 points. Why does this matter? Because as we make our steps smaller, as h right arrow 0, the error shrinks quadratically. That means if we have the step size, the error goes down by a factor of 4. That's fast convergence, and it's called OH2 accuracy. And here's the kicker, this works even when the points are unevenly spaced. Most textbook methods assume equal spacing, but real-world data. Not so neat. This method is flexible, robust, and built for the messy world we live in. So next time you see a simulation, a prediction, or a model that estimates how things change, remember, behind the scenes, clever math like this is making it all possible. Taylor expansions, linear systems, a little algebra, and a whole lot of precision. Thanks for watching. If you like this deep dive into numerical analysis, hit like, subscribe, and let me know in the comments. What kind of derivative approximation would you want to see next? Maybe third derivatives. Or maybe how this applies to solving real differential equations. Until next time, keep questioning, keep calculating.